Now, the analysis for all of these results comes to us actually from our hero, the Einstein. And his explanation came, and this is very interesting. His explanation came for these results in 1905, which really underscores what a genius he is, right? Because he is explaining all of these mysterious results 10 years actually before the experiment was done. Basically, Millikan was just doing a very beautiful and detailed exploration of the predictions of Einstein. And this, in fact, represents Einstein's Nobel Prize. Einstein never got a prize for relativity. He got it for this really amazing piece of theoretical physics. Now, his analysis, Einstein's analysis, is beautiful. It comes in two pieces. It has a qualitative part and a quantitative part. Now, the qualitative part is where a lot of the real genius goes in. He was able to explain all these mysterious phenomena with one simple assumption. And that assumption is that the energy in the electromagnetic field is delivered to the electrons in discrete packets of a fixed size, and that size E of those energy packets depends upon the frequency. Okay? So let's take a look at how this works. Now notice it's very important that these are discrete packets. It's not like a continuous delivery of energy, and they have a fixed size. Now, let's see how this explains things. So, if we try to look at, some of the earlier observations that were interesting. If we increase the brightness, that's increasing the energy that we are delivering to our surface per unit time. Well, in Einstein's picture, that's just increasing, or in our example, doubling the number of packets that we are delivering. Now, if you double the number of packets, it makes perfect sense, right? Each electron is sitting in here waiting for a packet to come. When he gets his packet, he jumps out of the material, right? So if we're delivering twice as many packets, it makes perfect sense. We get exactly twice as many electrons coming out. The other thing you can see is this explains why the energy distribution of the outgoing electrons, in other words, the shape of this curve, is unaffected by the change in the brightness, right? The shape is just multiplied by the fact we're getting more electrons out. But each electron is coming out with exactly the same distribution of angles and energies, and that makes total sense, right? We have all these atoms in here. We take one of those electrons, we deliver a packet to him of exactly the same energy, and it's not surprising then that the distribution of electrons that we get out is exactly the same, regardless of how many of these packets we happen to be delivering at any given time. And finally, this also explains why we can change the shape, right, when we change the frequency. Because Einstein is saying that the energy of these packets must depend upon the frequency. So now, of course, if we deliver a different size packet to one of my electrons, he's going to come out with a different amount of energy, and depending upon what atoms or whatever he has to bump into, because he's got more energy now, maybe he comes more straight out, so his angles and his energies are definitely going to be different. So that explains, and it also explains this mystery about the instantaneous nature of the phenomena, right? Because now it's not that the atoms are sitting there and waiting, right, to slowly build up enough energy in order to pop out their electron. No, what turns out is this energy is concentrated in these packets. So as soon as we start delivering some packets, some electrons, maybe not many, but some lucky ones get a packet, and as soon as they get that packet of discrete energy, they jump right out of that electrode. So this beautifully explains all of the qualitative pieces. Now, when we go to the quantitative part of it, this gets very interesting, because there is, by combining, right, the direct experimental evidence with this very simple but clear theoretical picture of what's going on, we can actually get direct information, direct experimental information, what this energy size of these packets must be. So here's how that analysis goes. It's basically an energy analysis. Let's think about what happens when we deliver a packet of energy. So we deliver this packet of energy to one of our electrons. Now, the electrons have lower energy, right? Lower potential energy for those electrons inside the electrode. And we know it must be lower in here because things naturally go to their lowest energy states, and the electrons like to be in there. They don't come out unless we invest some energy. So there is some change in energy for the electron to go from being in the metal to going out into that vacuum. So there's some cost then to get out into the vacuum that these electrons have to pay. Now, different electrons pay a different amount of cost because some might be more deeply bound inside of their atoms, or might be deeper into the material. Who knows? So this quantity can depend upon the electron. But what this is going to represent for us is something called the work function of the material. The work function is the energy needed to release the least bound electron. Okay, so this W that we're using, and this work function is definitely going to be material dependent, because different materials, of course, are going to bind their electrons with different amounts of strength. So when we subtract off the least amount of energy paid by any electron to leave our material, what we are then left with is going to tell us about the kinetic energy of the electrons coming out. But because we're subtracting off the least of the binding energies, we are getting the maximum kinetic energy that we should expect from any of our electrons. Right? So we deliver energy E, you pay this energy cost W to get out into the vacuum. What's left over then is your kinetic energy, or the maximum kinetic energy of any of the electrons. And this is the connection that we make from theory. But we can also, through experiment, make a direct measurement of this maximum kinetic energy. Because in the experiment, remember, that maximum kinetic energy is equal to the stopping potential, the potential at which we are able to stop all of the electrons, including the most energetic of them. So this is directly equal to that the energy associated with the stopping potential. Stopping potential is a voltage, so of course we have to multiply by charge to get an actual potential energy. And that stopping potential then, we have a direct experimental observation of it. And I can characterize that. This is the experimental connection. I can characterize EVS as a perfect straight line with a fixed slope. And so I will represent that as some slope, which I will call H. We'll discuss in a moment why it's called H. And then I'm going to multiply it by nu minus nu naught. So that when nu equals nu naught, I have 0. And then as nu increases beyond nu naught, of course, I then increase linearly. So this is simple theory and direct experimental observation. Now, things get interesting if we look at some of the connections in here. If we expand out this side, and turn it into h of nu minus h of nu naught, and compare the experiment to the theory, what we can see is the energy of these packets must be just h times nu. And that is a very nice relationship. H is a universal constant, and nu is a very simple property of the electromagnetic field, so it seems to make entire sense that what we're looking at here is some kind of fundamental law of physics that has something to do with light. And this is a nice universal law as well, because it's completely independent of the material. So we seem to have a nice, beautiful law of physics here. The second piece, of course, that we can identify is the work function. The work function itself must equal Planck's constant h times then this nu naught. Now, nu naught was material dependent in our observations, and that makes complete sense because, of course, the work function also we would expect to be material dependent. So this, again, just really depends upon our material. Whereas this first relation seems to be extremely fundamental. We know it's universal, it doesn't depend upon the materials used in the experiment, and it also has that very simple form that rings true for a true, a fundamental law of nature. Now, in regard to that constant h, this constant h has a particular value, right? You can extract it directly from Millikan type experiments. Its value is 6.6 times 10 to the minus 34. That's the numerical value. For the units, I hope you'll see, right, I have to multiply this slope times a frequency to get an energy. So I need something that when I multiply by frequency gives me energy. Well, frequency is divide by seconds. So the units of this thing have to be energy times seconds, right? So that when I multiply by inverse seconds, I get energy. So the units on that slope actually are in joule seconds. And this constant has a very famous name. It is known as Planck's constant. And naturally, we're going to be using this quite in depth throughout this course. So the bottom line lesson here, if I wanted to really kind of summarize all of this discussion for us. So the lesson is that the energy from the E&M field seems to be always delivered in discrete packets of energy of a fixed size, and I usually will write this as epsilon, and that energy is h times nu. So that is our first introduction then to this new concept about light consisting of these discrete packets, and this is what is known as a photon. Very good. So that then ends our discussion of this topic.